Hello dear students, welcome back to the tetrahedron chemistry classes. So in today's class, I am going to discuss a very important reagent, and the name of the reagent is the lithium diisopropylamide, and the acronym for that lithium diisopropylamide is LDA, right? So this is the structure. Two structures I have drawn here for this LDA. Okay, first one, there is a covalent bond between the nitrogen and the lithium atom, and in the second, the ionic interaction or the ionic bond is there in between the nitrogen and the lithium atom. As you know from the Fajan's rule, no bond is perfectly ionic and perfectly covalent, so it will not make any difference whether I will write my lithium nitrogen bond like that, or simply I put the negative on the nitrogen or positive on the lithium. It will not make any difference, and the formula is LinCH 3 times 2 whole twice. So this is this is your, basically this one is your isopropyl group. Okay, how this is your isopropyl group, you can very easily number this substituent 1 2 3. Three carbons are there, so it's a propyl group, and from the second carbon it is connecting with this nitrogen, so it's basically it is the isopropyl group, and this isopropyl group is present two times. That's why diisopropyl is there, and this is the nitrogen with the negative sign. It's a derivative of the amide. That's why amide is also there and lithium is there. Okay, and now we'll discuss why this this LDA is very important, and what are the different reactions that can be given by this LDA. Okay, and what is the importance in the organic synthesis of this here LDA. Okay, so first of all, you should remember it's a very strong base. Please remember, it's a very strong base. Okay, and it is much stronger than your hydroxide or your any alkoxide ion. It's a very strong one. Okay, and due to the presence of these two bulky isopropyl group, it's a hindered base. Hindered base means this nitrogen is basically is overcrowded with these two isopropyl groups, and since it is a very bulky in nature, very hindered, and this hindered nature is basically due to this bulky group. Okay, so it's a bulky strong base, because this nitrogen is hindered. When it is a very bulky in nature, so it's a very poor nucleophile, almost non-nucleophilic in nature. Okay, but it can act as a nucleophile, but under a very special circumstances. But mostly it is used as a non-nucleophilic strong base. Please remember this one, right? And please remember one thing: whether you are considering your acidity of acids or the basicity of the bases, so whatever the bases or the acids are there, if they are very heavy or the bulky in nature, so they are very slow reacting. So please remember, this LDA is slow reacting. Please remember, it is slow reacting, and whatever whenever your reagent is reacting very slowly, then it would be very highly selective. Okay, highly selective, and since it is very highly selective in nature, so this LDA is very beautifully used in the di-stereoselective synthesis. Please remember, selectivity would be very high. Okay, and basically this reaction, this LDA is very ideal for promoting E2 elimination reaction. We will see in a little while, and there are enormous number of applications in the organic synthesis or in the natural product chemistry, right? Whenever you synthesize the natural products and many other things, enormous numbers of applications are there, but we will discuss very few important applications of this LDA. And from this particular topic, the questions generally are there in your CSIR net examination as well as in your gate examination. So what are the different applications you should see here? First of all, we will do the alkylation reaction, right? However, the reaction will start with this one, right, with this LDA, and after LDA we will introduce the alkyl group. That means we can very easily form carbon carbon bond. So formation of the carbon carbon bond using this LDA is a very important applications of this LDA, lithium diisopropylamide. And whenever you do the crossed aldol condensations, then the importance of this LDA is very high, because when you do your crossed aldol condensation reactions with the help of the your strong base like hydroxide ions or ethoxide ions, then there are lots of problems. Okay, so we'll discuss those problems in a little while. So but if you don't know what is the aldol condensation, I have uploaded 3 videos on the aldol condensation in the pretty much detail, where I have discussed the different aspects of the aldol reactions, and I'm giving you the link in the description box, and also link is flashing at the top, or it will flash in a little while at the right top of your screen, the link for this aldol reactions. Okay, and then ester condensations or ester aldol reactions can also be initiated with this your lithium diisopropylamide. If you use the different kind of the reagents, then there are lots of problems. You should remember these things. This is very, very important. Okay, now moving to the next slides. Now, since this LDA, lithium diisopropylamide, is very, very important in the carbonyl chemistry, and this carbonyl chemistry basically belongs to the aldehydes or the ketones basically. So we'll discuss the aldehyde and the ketone chemistry, and where we'll find the various applications of this LDA, and particularly we will form the lithium enolates in that case. So before going into the details of the lithium enolates, you should know what are the enolates. As the name suggests, en, that means the presence of the double bond, and enolates means that mean oxygen with a negative sign should be there. And these enolates basically are formed by the removal of the alpha hydrogen from the carbonyl compounds, right? If your carbonyl compound is having the alpha carbon, that means enolizable carbonyl compound is there, then definitely you will form the enolate. So first of all, I am taking this very simple general example. This is the R, which is any alkyl group. If you take this CH3, then it would be your acetone. If you take your C2H5, then this would be your butanone, right? And since though I have written only R there, because I'll use this CH3 group over there, right? And from the basics of the chemistry, the carbon which carries the functional group is basically the carbon which is your this one, C double bond O, and just next to you are having this carbon which is known as the alpha carbon. So carbon which is present just next to the functional group is known as the alpha carbon, and this alpha carbon is having 3 alpha hydrogens to this one, and third one I have shown in a different way, because I needed this particular hydrogen to show in that manner, right? uh, you see, this is my R, this is O, and this is CH3. So these hydrogens are like that only, but I have shown this hydrogen in that particular manner because I'll remove that hydrogen from this position. Okay, so enolates are formed by the removal of the one of the alpha hydrogen from the carbonyl compound. So this is your, these 3 are the alpha hydrogens, and with the help of any base, right, you can take your hydroxide, you can take your ethoxide, you can take, see, potassium hydroxide, sodium hydroxide, sodium ethoxide, potassium ethoxide, you can take this one, or if you want, then you can take the bulky bases as well here, like LDA. But initially I'm writing this only OH here. So what this OH will do, this OH negative will grab hydrogen from here as a proton. Please remember, this hydrogen will be removed from here as proton. Alpha hydrogens of the carbonyl compounds are acidic in nature, so there is a acid base reaction between the two, and the water molecule will remove from here, right? So what I can do, I can write minus H2 over there. Okay, and then you can see, when I remove this hydrogen as a proton, this bond will be shifted onto this or in between this carbonyl carbon and this alpha carbon. So this will make a double bond, and this will go up. So this you can see I have drawn here, and in the final structure, see, this is resonance stabilized. How resonance? This negative charge, which actually comes by the delocalization of this particular uh, electron pair onto this carbon atom, and this will come here, this will make double, right, between carbonyl carbon and this particular carbon, and this will move up, right. So this species is basically your enolate, in and negatively charged oxygen, and this is resonance stabilized. Okay, and please remember, these enolates are of 2 kinds. Basically, we can classify the enolates in the 2 ways. First is your thermodynamic enolate, and second one is the kinetic enolates. And generally, most of the chemistry of the carbonyl compounds are done by this kinetic enolates only. Okay, though they are not very stable, but they are stable enough to be used in the organic synthesis. Please remember. Okay, so how we can differentiate? See, if you have the question in your examination, right, where you have to find the thermodynamic and the kinetic type of the enolate, then you can consider some of the factors. The enolate which is the more substituted one, right, that would be your thermodynamic enolate. Okay, that means the substitution on the carbon, if is very high, if the substitution on the carbon is very high, then it would be your thermodynamic enolate. And when the substitution is very less, then it is your kinetic enolate. Okay, and this thermodynamic enolate, you know, thermodynamic parameters actually accounts for the stability of the reactive intermediates. Okay, so it's a reactive intermediate, please remember. Okay, kind of, not exactly, but kind of reactive intermediate. Okay, and it is more stable in nature, but your kinetic enolates are very less stable. Okay, and if you want to make your thermodynamic enolate in your solution, then you need to use the excess of the carbonyl compound. Whether you are using the ketone or your aldehyde, you need to take this ketone or aldehyde in the excess, and high temperature is required. High temperature means either you will do your reaction at RT, that is room temperature, or it may jump up to 35 degree. So 25 degree centigrade to 35 degree centigrade temperature is required to form the thermodynamic enolates, and long reaction time is needed for this one. Please remember, long reaction time is needed no long reaction time is needed to form the thermodynamic enolate. This is something very important. Okay, then there comes the your kinetic enolates. They are favored by the strong base, strong hindered base, right, and low temperature is required, and most of the reactions of the lithium enolate especially, you will see it will occur at minus 60 to minus 78 degree centigrade. Okay, this would be the temperature. Negative temperature favors the kinetic enolates. Okay, and very short reaction time is needed to form these kinetic enolates in the solutions, and the bases you will require for the formation of the kinetic enolates are LDA, lithium diisopropylamide, which I am discussing tomorrow, sorry, which I am discussing today, right? And then your LiHMDS, I'll discuss this later on, and then PH3, C negative, Na positive, and then LiTMP. We'll discuss these things in separate lecture, but today I am going to discuss this LDA only. And for the formation of the thermodynamic enolate, you need only simple strong bases like sodium hydroxide, your potassium hydroxide, your sodium ethoxide, or the combination of the potassium hydroxide with the ethanol, or sodium ethoxide with the ethanol. Okay, so these combinations basically give the thermodynamic enolates, while these bulky, hindered, very selective strong bases will form the kinetic enolate. Please remember, this is something very important. Okay, and then you see how we can form the different kinds of the enolates. It's quite easy. So first of all, okay, then why LDA? Why LDA? That means, what is the meaning of the of using this LDA? So I'm telling you, say for example, you are having certain carbonyl compound, right? You are having CH3, C double bond O, and CH3, right? And you are reacting it with a very strong base. Okay, and say your RT is there, room temperature is there, then definitely you are going to produce this particular species where CH2 negative is there. Okay, this thing you are doing here. So what will happen in that case? If you have taken this 10 raised the power 4 part of this your acetone, then out of this only only one part will be converted into this enolate while using this OH negative. But if you do the same thing with the LDA, right? If you do the same thing with the LDA, then there is quantitative conversion. So I am writing quantitative conversion of carbonyl compounds into the enolates. Quantitative conversion of carbonyl compounds to enolates, right? This is the first advantage. And second advantage is there, if there is a possibility of producing the diastereomers, then the selectivity of this LDA would be very, very high in comparison to the normal bases. So this is very, very important. Your LDA, lithium diisopropylamide, quantitatively converts the carbonyl compounds into the enolates, while the strong bases like your hydroxides and others, right, they however they are not they are not stronger than the LDA, but they also do the same thing, the conversion of the carbonyl compounds into the enolates, but to a very limited extent, as I have explained to you. Okay, and this lithium, if you form this lithium enolate, so this is the structure for the lithium enolate. Say CH3, C, O, Li positive, negative, and double bond, and this is say your CH2. This is your lithium enolate, and this lithium enolate is basically stable at very low temperatures, minus 78 degrees centigrade, but they are reactive enough to be used in the organic synthesis. This is the importance of the of using LDA in the different kinds of the reaction. Okay, I hope this is quite clear to you. Now I'll discuss how we can form these enolates and what is the mechanism of forming the lithium enolate. So from now onwards, I'll discuss only my lithium enolates. Lithium enolates, right? I'll discuss only this lithium enolate. And say, for example, you are having this species. See, I'll not write the name of the compounds every now and then, because this is not the lecture of IUPAC nomenclature. I simply draw my structure of the compound and do the reactions. If you want to write the IUPAC name, then you can go for the IUPAC nomenclature by tetrahedron chemistry classes, right? You can search in the YouTube IUPAC nomenclature by tetrahedron chemistry classes. I have made a I have uploaded the videos on the IUPAC nomenclatures, right, of bicyclic compound and different kinds of this spirase and the spiro compounds, right? If you want, then you can check there. But right now you can focus only here. See, this is your basically what? Carbonyl compound. This is your ketone, and this carbon is the alpha carbon. I am writing here, it is the alpha carbon, and this is your second alpha carbon, right? And you know this alpha carbon is having hydrogen from here, and these two alpha hydrogens are also present on this particular carbon atom. Okay, and intentionally I'll use only one of these two hydrogens to form the lithium enolates. I'll not touch this particular hydrogen to form the lithium enolates, and the reason is quite simple. If I touch this particular hydrogen, I need to put double bond on this bridged carbon or bridgehead carbon atom. This will violate the Brett's rule. So I'll not put that double bond from here. That means I'm not going to touch this particular hydrogen. Okay. So what will happen now? You see, say you are having this particular lithium atom. It is connected with the nitrogen. This nitrogen is very basic in nature, which is responsible for the basicity of LDA. Right? This species is there. So what will happen in that case? In the first step, what will happen? This double bond will grab this lithium atom, right? And when this, see, this is the step number one. Please remember, this would be the step number one. Your carbon double bond oxygen, the double bond which is present between the carbon and oxygen, will actually attack on the lithium atom and grab the lithium atom from there. And then this negatively charged nitrogen, right, this one, this negatively charged nitrogen, this will grab one of the hydrogen from here as a proton, and this bond will be pushed back into the cyclic system. Okay, and then you will have your uh, lithium enolate, right? So this is your structure, just like that. I'm drawing it again, right? And you see, this will become now O and Li. Li is positive, oxygen is negative, and this is the double bond. So this is your lithium enolate. And what will happen? Your nitrogen, which has grabbed hydrogen from that carbonyl compound, will now we will now form this particular compound, which is your NHR2, where your R is the isopropyl group. R is the isopropyl group. Because I don't want to write this lengthy structure again and again, that's why I have used this R2. Please remember, this is very, very important. And one very important thing is that which you should always remember: this bond between the oxygen, see, this is the ionic bond, it is a very strong bond, which it is the very strong bond. So first of all, this bond will form, and after that your basic nitrogen will grab the hydrogen from the carbonyl compound, alpha position of the carbonyl compound, to form the enolate, right? This is very, very important. The correct mechanism is this. I hope this is quite clear to you, right? Now what we will do, we will do the various numbers of the reactions based on this one. Since I have explained this particular mechanism here, how actually your LDA remove the hydrogen from this alpha position, so I will not draw this entire mechanism again and again for the n number of the reactions, but you should remember this particular point, how actually I have drawn this one. And okay, so now moving to my different kinds of the reactions, how actually the reactions are taking place. So for this, say for example, I am taking this first example. Say this is my reaction number 1. I am writing here my reaction number 1, and in this reaction number 1, I am having, say, this particular carbonyl compound, which is your cyclic ketone, and that cyclic ketone is having the substitution of this CH3. Okay, and what actually I am doing here, say for example, let me take this LDA first. So LDA means I am taking this lithium, nitrogen, and R2 I am writing instead of your isopropyl group. Okay, so what will happen in that case? Again, it's quite simple for you. See, one alpha hydrogen is present here, and two alpha hydrogens are present here. Okay, now please listen very, very carefully. This is very, very important. Two hydrogens are available on the left hand side, and two hydrogens are available, one hydrogen is available on the right hand side. Now this which hydrogen actually will be grabbed by this basic nitrogen is a very important question. Okay, since this LDA is a very bulky in nature, sterically hindered, bulky in nature, slow reacting, highly selective, and this methyl group is present here, and this hydrogen is basically is overcrowded or sterically hindered with this methyl group. So your LDA will not go to grab this particular hydrogen, but that nitrogen actually will grab one of the hydrogen from these two which are present on the left hand side of your cyclic system. Okay, so how the reaction happen in that case? You see, this will grab this lithium, okay, and then this negatively charged nitrogen will grab one of the hydrogen from here, pushing this bond over there, and this will come up, and finally it will grab the lithium. Okay, and then you will form your compound, and your compound would look like this cyclohexane ring, and double bond is there. This is O negative with the lithium, that is positive here. Okay, and your CH3 is here. If you want, then you can form the resonance structure of this one, but I am not going to form the resonance structure. Okay, now say in the second step, I am having this species, for example, like CH3. Okay, CH3I is there, CH3I is there. So what will happen? Your alkylation is taking place in that case. How the alkylation will take place in that case? You know, what will happen? This will come back onto this particular position, and this will come here, and this electron pair will grab this CH3, right? Because this electron pair is coming here, and this electron pair is enough to form a covalent bond with this methyl group. So this bond which is present between the CH3 and the I, this bond, this electron pair or the bond is not required by this CH3 to form the bond with this particular carbon. Okay, and what will happen in that case? Then this negatively charged species will grab the lithium from here, that means minus LiCl, and then you will have your product, and your product would be your CH3 here, and this is another CH3 here, and this is your carbonyl compound. So what you have done here, you have introduced or you have formed this new CC bond, This is the very important application of this LDA when you want to introduce a alkyl group or you want to form the new carbon-carbon bond, then this reaction goes very well. Okay, so this is something very important you should know, right? Or simply see, this is the mechanism. Now one thing you will always remember whenever you are using the LDA, of course minus 78 degrees centigrade, I forgot one thing to write here, minus 78 degrees centigrade would be there, and whenever you use the LDA as a base, your tetrahydrofuran will be used here. It's a heterocyclic compound, tetrahydrofuran. Okay, 6-membered ring, one oxygen is there and hydrogens are not there. THF, right? I am not going to draw the structure of the THF. So these two conditions generally, in place of the THF, DME can also be taken as the solvent here, but most generally THF would be there in this LDA system. Okay, so this is something very important. Now this is the entire mechanism, and this reaction is basically the alkylation reaction. This reaction is the alkylation reaction, right? This is the entire mechanism, but you can very quickly remember this thing here. Whenever you are having the carbonyl compound like that only, and if you are doing this reaction with the LDA, okay, and minus 78 degrees centigrade is there, and of course your THF as a solvent, this is the first case, and in the second step you are taking say your CH3I, then your product is nothing but it is your substitution of the methyl group on the alpha carbon which is less substituted. Please remember where I have placed this particular alkyl group, on the on the alpha carbon which is less substituted, right? This is more substituted. So this is very important. In short, if you want to do the reaction, then if you see this particular system here, this is the alkylation, then you immediately place your alkyl group on the alpha position which is less sterically hindered or the less substituted. In this way you can do your reaction. I hope this is quite clear to you. Now very quickly what we can do, we can check another reaction, and my second reaction is also alkylation reaction. Okay, my second reaction is also alkylation reaction, and you are having this species. This is your carbonyl compound. Okay, and this is substitution here, and this is OET. This is your starting material. Okay, and now you can see here, this is your alpha carbon, this is your beta carbon, and this is also the alpha carbon. Please remember. Okay, so this is your alpha beta unsaturated carbonyl compound. Okay, this is your alpha beta unsaturated carbonyl compound. Okay, one hydrogen is there. Okay, and two hydrogens are there. You can see here two hydrogens are there. Okay, and then you can see here you are doing the reaction with this LDA. What you are doing, you are taking your LDA, okay, and you are keeping your temperature at minus 78 degrees centigrade, and you are taking your THF tetrahydrofuran. Okay, and this is the first step. In the second step you are doing this methylation under the same conditions of the temperature and the solvent. So now, as I already told you, you will always put the methyl group on that position which is less substituted, but in that case you can see here the substitution is quite fine. Okay, quite same in both the cases. Now it is up to you whether you put the methyl here or here, but logically you can see here, this your LDA, this LDA actually is what, the your strong base, and it is a negatively charged species. Nitrogen is negatively charged. If I write this again, nitrogen is negative, lithium is positive, and say your R2. So this is negatively charged species, though this hydrogen is positively charged, but this double bond is also there, and this crowding is also there. So this hydrogen cannot be grabbed by this your LDA, but one of these hydrogens will be grabbed. Okay, so what would be your product? Your product would be this species, double bond O, this is this OET, and then you put your methyl here, CH3. So this would be your product, right? So there are different kinds of the reactions, right? You can do the reactions and you can understand the general organic chemistry as well. See, if you don't know how to apply the different concept like your inductive effect, mesomeric effect, resonance, right, and steric hindrance, formation of the carbocations and anions, if you don't know all these things, then definitely you will face difficulty in solving the organic chemistry problem. So this is another alkylation reaction which is quite simple one. Okay, and in the third case, right, this compound is there. Okay, and what I'll do, I'll react this compound with the LDA. So LDA I am writing here. At this particular position, you are having the two alpha hydrogens. Though this is not the carbonyl compound, please remember, it's a EJA compound. This is imine compound. Nitrogen double bond is there. That means it is a imine compound. Okay, and you can see again here, this is one of the hydrogen which is present on this particular center here, right? But it is not a very good idea to remove the hydrogen from this cyclic system, right? So we'll remove hydrogen from here. We'll grab this lithium. Okay, and when this bond will form, then this nitrogen will grab this particular hydrogen, one of the hydrogen basically, right? And this bond will be pushed back onto this particular position. Okay, so this came here, please remember, see again, this will come here and that will grab the lithium from here, and then your nitrogen will grab hydrogen from this alpha position, right? And this bond will be pushed back onto this particular position when you use the LDA. Okay, and then you see the intermediate, what kind of the intermediate you are going to form here. Say this is your R now, and this is species, now we are having a double bond here, and this is your nitrogen connected with the lithium, and then here this species, right? So this is your lithium as a enolate, lithium as a enolate species, this species. Okay, and finally, say if you want to do reaction with this one, say this compound I am taking here, 1 2 3 4, 4 carbons I am taking, and I am substituting it with the Br, and for this it is essential to give the number 1 2 3 4, 4 carbons are there. So this numbering is not according to the IUPAC, please remember, this is only for the explanation how I'll do the reaction. Okay, so what will happen in that case, you know, this Br is a very better, very good leaving group, so this will leave from here. And how this will leave from here, this is something very, very important. So this group will leave along with this electron pair, that means it will going to grab this lithium. So minus Li Br would be there. Okay, and this particular carbon number 4, this particular carbon number 4 will attack onto this particular carbon atom. Okay, and then you will form your compound. See, now see carefully how actually I am writing my compound. This is very, very important. R is there, right, and this carbon is there, and just like that you see this is there, and this double bond will be here, nitrogen, and then your 6-membered ring, and onto this particular position you are having the substitution of the 4 carbons. So first of all I am writing 1 2 3 4, this system, right? So what will happen, see again, I am going to explain this one. This will be removed from the negative, this Br will be removed from here as a negatively charged species. This will going to grab this lithium, and when this lithium will be grabbed, this bond will be pushed back over there. Okay, and I made a mistake here. I made a mistake here, and then this electron pair which will come here, this will grab this particular bond. So earlier, in the earlier case, what I did, I moved the electron in the wrong way. But actually what is happening here, this Br is removing from here as a negatively charged species. This though is, so it is positive, right? When lithium will be removed from here, this will be pushed back over there, double bond, and this double bond will be pushed back onto this particular carbon atom, and then this electron pair will grab this 4. Okay, so this actually substitution is actually occurring on this particular carbon atom. If I want, then I can number it as well. Say this is 1, this is 2, this is 3, this is 4. So 1, you can see here, and say this is your 2, and this is your 3, this is your 4, and you can see here the substitution is taking on the carbon number 3, and the substitution is taking on the carbon number 3, right? And 4 carbons, 1 2 3 4 carbons are there, so I added 4 carbon to it. Again, this is the alkylation kind of the reaction, but it is happening with this lithium as a enolate. Very important reaction. So not only your carbonyl compounds, but your immune system, this is your immune system basically, this will also do this particular kind of the reaction, right? And finally, if you do the protic workup, or simply I can do the hydrolysis, I can do the hydrolysis of this one, imine hydrolysis. What I am doing, I am doing imine hydrolysis. I am not going to discuss the mechanism of the imine hydrolysis, because it is a little bit of complicated, and it will take much more time, right? So, and the length of the video will be increased. So I am straightforward writing the product, but in a separate lecture I will explain the hydrolysis of the imine as well. But you will remember, you will always remember this particular point whenever you do the imine hydrolysis. That means this doubly bonded carbon which is connected to the nitrogen, this will be converted into the oxygen actually, so you will get the aldehyde. So what product you will have in that case, I am writing your product R, and this would be now double bond. Okay, and here you see the substitution would be like that, and of course I have converted this one, and in order to complete the valency, this would be your hydrogen. So basically you are producing what, you are producing your aldehyde, you are producing your aldehyde. Okay, so this is how you can do your reaction. Okay, number of carbon atoms, if you want, then you can check. This is 1, this is 2, this is 3, this is 4, and here again you see this 4 carbons are there, these 4 carbons are there, right? It is always a better idea for the beginners to number the carbon chain whenever required. Otherwise you will end up with the wrong result, right? It's a good practice, right, to put the numbers on the systems. Very important one. I hope this is quite clear to you. Now say for example, what I can do, I can take some more example, like say this one, and I am writing my problem number 4. Very quickly I can do the numbering for this system as well. Okay, how I can do the numbering for this system? 7-membered ring is there, right? And say my first reagent in that case is your say sodamide, just like that. Okay, you know sodium is positive and this is negative, right? And this nitrogen is electronegative, this hydrogen is there, so this is the polarized bond, this hydrogen is having the positive charge on it, so this hydrogen is acidic in nature, it is much more acidic than this particular hydrogen, please remember. So you have option actually from where you can remove the hydrogen from here, this carbon, or you can remove the hydrogen from here. But if you compare the acidity of these two hydrogen, then you will find this NH is this hydrogen which is connected to the nitrogen is much more acidic, because this bond is polarized. This is having the positive, more positive character compared to this particular hydrogen, which is which I have not written over there, but you know the two carbons are hidden there. Okay, so what species you will get here? Now again, I'll draw my 7-member ring very beautifully. This, 2, 3, like, and this is my carbonyl, and connected with this N here. And of course, what will happen actually? You see, this is the species basically which will react. This will attack onto this hydrogen. No problem in that. Okay, and this electron pair will be pushed back here, and this will back here, just like that. Okay, so I need to correct this one, I need to remove this one. Okay, and then you see this N would be there, and this would become double bond, and this negative charge basically which came here, this will grab this particular sodium. So basically this sodium would also be there. I am writing this sodium. This intermediate actually I am having, you know, this is negatively charged, this is positively charged. Okay, and your 7-member ring is there. Okay, and suppose now what I am doing here in the next step, tosylate into the better leaving group. You know, this is your tosylate ion, right? Paratoluene sulfonic acid, right? It is basically tosylate ion comes from there, and it's a very good leaving group. Please remember, it's a very good leaving group because it can accommodate the electron pair beautifully on it. So it's a very good leaving group. So what will happen? There is a bond between oxygen and this methyl. So this will come back onto this one. Okay, and that will grab this methyl. Okay, and this tosylate will be removed from here, and then this will come here, right? So what you will have here, you will have NaOTS negative. That means this sodium will combine with this one, NaOTS will be removed from here, and this nitrogen will get the Me. So basically you are doing the alkylation on the nitrogen atom, and pushing back this electron pair to give the original ketone back. Okay, and your product would be, you see again, 7-membered ring. Very beautifully you can draw. This is your double bond, and this is your nitrogen having the substitution of the methyl. Very, very important. Okay, very important. This is CH3. Now here you can see what I can do. I can use my LDA. I can use my LDA, lithium diisopropylamide. This chemistry is there. Now you can see, this is your alpha carbon which is having the 2 hydrogen. This is your nitrogen on the alpha position, but it is not having any hydrogen because nitrogen is having the valency of 3 only. So this LDA is left with only one option to remove the hydrogen from here only. Okay, so what I am doing, I am drawing only one hydrogen from here. Okay, so now the mechanism, you know, it's quite simple. Mechanism is quite simple. uh, the lithium actually which is present here, so I am writing Li here, will be grabbed there, and then the hydrogen will be grabbed, and this will be pushed back here, right? I have drawn this so many times, so you now you have an idea actually how we can do this one. So this will be O, Li positive, O negative, and this bond is here, and this is your nitrogen, and then CH3. That means you have produced enolate here, lithium enolate you have produced over there. I think there is no problem in that. And then you can simply do any kind of the reaction, any substitution of the alkyl group onto this one. So for example, red is not looking very, very good. So I am taking, say, CH3, CH2, Br. Okay. Now it's quite simple. This bond will be removed from here. This will taken back, and this will be pushed back here, this will come here, and it will grab your ethyl group, and this will, when this will grab your ethyl group, then you will have this particular compound as a final product. Okay, and you see this double bond oxygen, okay, and nitrogen with CH3, and your ethyl substitution onto this particular position. So again, what you have done, you have produced this new CC bond, new carbon carbon bond, right? And it's a 7-member reaction. So these are the problems I have taken from the Claydon. These problems are there in the Claydon book, right? Warren, Walther, and Claydon. Stuart Warren sir have written that particular book, right? Stuart Warren, you know the disconnection approach by the Stuart Warren, very famous book. So the Claydon book is also very, very famous. One of the author is where Stuart Warren sir. Okay, so I have taken this particular problem from there. I hope this is quite clear to you. And not only these reactions, but sometimes the cyclization reactions are also there. Very, very important cyclization reactions are also there with this LDA. So we can take the example, this was my reaction number 4. Now say my this reaction number 5. Okay, and you are having this 5-membered ring, this, okay, and here the ketone functionality is there, which is your CH3. There is no problem in that. And then you are having your CH2, okay, and say it is 3 times, that means propyl group is there, and your Br is there, okay. And say for example, if you are doing this particular reaction, and your LDA you are using, and minus 70, or in that case not 70 but minus 60 degree centigrade is given here, and you are using say THF, right? So whenever you see this minus 60 degree with LDA and THF, then it's a kinetically controlled product. So I can write Kp here, kinetically controlled product. In the earlier ones as well, I need to write in this particular step, this is your kinetically controlled product, okay, Kc, or I'm writing Kp, okay, minus 78 I have to write over there. And in the previous examples here, again they are what? They are your kinetic product. And as I already told you in the beginning of the lecture, your lithium diisopropyl chemistry is basically generally done in the kinetic control, okay. So now this problem is there, okay. And what will happen in that case? You see, I'll produce the lithium enolate from here. Now say this is what? Your carbonyl group, and one substitution of methyl is over there. This is your alpha carbon. So I am putting my alpha here, and then you can see this is also alpha here, okay. And one of the hydrogen is also there. But now you have the better idea. This LDA is very bulky base, strong but bulky, and this hydrogen is basically overcrowded with this propyl group. So this LDA will not going to grab this particular hydrogen to form the enolate, but it will grab some other hydrogen, and that hydrogen would be your CH3 hydrogen, okay. And your product would be your intermediate, not product exactly, your intermediate would look like this is your 5-membered ring, and here your CH2 times 3, okay, and your enolate will form. Enolate, you know, now this is OLI negative, so I'm not writing the mechanism here again. And double bond, this is CH2, this is your enolate which I have produced over there, okay. And now you can see here what we can do in that case. See, we can do the cyclization. We can do the cyclization. See, in the first slide, if I go back, right, very quickly, if I go back, right here, what I have written here, ideal for promoting E2 elimination. So though I didn't mention in my previous problems, but in this particular problem I am going to discuss that E2 elimination kind of thing. Say this is Br, Okay, so cyclization will occur due to the E2 elimination by the E2 fashion mechanism. Okay, so how the cyclization will occur? For this, you need to number this species. Say this is your carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. Okay, and 3 carbons are there, so 7 carbons are there. 7 carbons are there. Okay, 4 and 3, 7 carbons are there. That means you will form the 7 membered ring. So how we can form the 7 membered ring? This 5 membered ring is there in the system already. Okay, and what will happen in that case? You see, uh, this will be removed as a negatively charged species from here, and lithium will go along with this Br. So minus Li, Br would be there. This will be pushed back, and this will come here, and this will going to join with this 7th number of the carbon atom. 7th number of the carbon atom. So you have produced this here, and then you can draw your 7 membered ring. Say this is 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is carbon number 5, this is carbon number 6, and this is carbon number 7. Right, though the drawing is not very good, but it is quite enough to understand how I have produced 1, 2, 3, 4, 5. Not this one, this is directly connected, I am sorry. So I have introduced, or I have drawn one extra bond, 5, 6 and 7. So it's a 7 membered ring which you have produced here. So your cyclization is also taking place. Okay, so you can see the whenever you want to form the cyclic compound, then again you can use this LDA very beautifully. So there are numbers of the reaction which you can do by your own. Okay, and this is simply alkylations and all these things. Now I am going to discuss another very important part for this, the aldol reactions. So as you can see, the length of the video actually increased so much, so I am stopping my lecture here only. This is the first part of the LDA reagent, and in the second part I will discuss the Zimmermann Trexler model with the various examples and the other applications of the uh, LDA reagent. Okay, so please stay tuned for the next part as well. Okay, so that's it for today.